All right, we looked at several different ways to represent relations or functions. We've looked at domain and range maps, like this guy. We've looked at tables relating x and y values. We've looked at lists of ordered pairs, and we've looked at a graph. All of these are different ways to represent relations or functions. And now I want to talk about something called functional notation. Functional notation is a shorthand way of describing a function. So you've probably seen something like this before. So for example, f of x equals 2x plus 3. This is an example of functional notation. And in particular, this is the part that makes this functional notation. Now, what is functional notation doing? It's giving us a function or an equation that's describing the relationship between the x values and the y values. The important thing to remember here is f of x is standing in place of y. In other words, I could also write this as y equals 2x plus 3. So what's the advantage of writing this as f of x as opposed to y? Well, functional notation just has some nice shorthand, okay? So if I have this written as f of x equals 2x plus 3, okay, and I want to know what happens when x, so what do I get when x equals 0? Well, that means I'm plugging in x equals 0. I'm doing 2 times 0 plus 3. Well, instead of having to write what do I get when x equals 0, functional notation lets me ask what is f of 0? That's literally saying take this x, replace it with 0 everywhere in your equation. Okay, and what is this? Well, 2 times 0 is 0 plus 3 is 3. So f of 0 is 3. That's telling me that I have the ordered pair 0. X is 0, y is 3. Okay. Similarly, I could ask something like, what's f of 1? Well, f of 1 means everywhere up here that I have a 1, or sorry, everywhere up here that I have an x, I'm going to replace that x with 1. So f of 1 would be 2 times 1 plus 3. 2 times 1 is 2, plus 3 is 5. That tells me the ordered pair 1, 5 is a part of my graph. Okay. Now, functional notation is going to be really important as we move on. We're going to use it a lot. Okay. And one thing that I like to do that's kind of nonsensical to help us remember what we're talking about when we're talking about functional notation is ask a silly question like this. What would f of smiley face be? Well, the key thing to remember about functional notation is it takes whatever's in here and replaces all of the x's with that. So if f of x was 2x plus 3, f of smiley face is 2 times smiley face plus 3. This is mathematically meaningless, but it helps us see what functional notation is doing, okay? We're going to use functional notation a lot in this class, so I do want to do at least one more example of it. So another thing I like to say when I'm talking about functional notation is functional notation is sort of a naming feature, right? If I say f of x equals 3x squared plus 2x plus 4, well, this is saying this expression, 3x squared plus 2x plus 4, I've named f of x. So as opposed to saying 3x squared plus 2x plus 4 all the time, I can just say f of x. Now, the other big advantage to functional notation is it lets me quickly do some calculations. So for example, if I want to know what f of 1 is, that means everywhere up here that I had an x, I'm going to replace that x with 1. Okay. Oftentimes when I do that, I remind myself by saying, okay, all of my x's are going away. So instead of x squared, right now I've got blank squared, 2 times blank. And I'm replacing those with 1. So this becomes 3 times 1 squared plus 2 times 1 plus 4. And I'm going to simplify. 1 squared is 1. 1 times 3 is 3. 2 times 1 is 2 plus 4. 3 plus 2 plus 4 is 5 plus 4 is 9. So f of 1 is equal to 9. Similarly, we could do f of, say, negative 2. Okay? That would be 3 times negative 2 squared plus 2 times negative 2 plus 4. I'm just replacing all of my x's with negative 2. I'm going to use order of operations to simplify this. Order of operations says we do parentheses and exponents first. Negative 2 squared is negative 2 times negative 2. That's positive 4. Positive 4 times 3 is 12. 2 times negative 2 is negative 4 plus 4. 12 minus 4 plus 4 is 12. So that tells me that f of negative 2 is 12. And last, even though it is mathematically meaningless, going to help us later on. I want us to think about what f of smiley face would be in this case. Well, if f is defined like this, 3x squared plus 2x plus 4, f of smiley face literally means every place that I had an x, I'm going to replace that x with smiley face. Okay, so that becomes 3 smiley face squared plus 2 times smiley face plus 4. Mathematically meaningless, but again, it's going to help us remember what functional notation means, which will help us later on when we really use functional notation for things like composition and decomposition of functions.